All right, good morning, everybody, and welcome to another CSL seminar. This morning, we have Jacob King, who is a master's student in CSL, and he's actually going to graduate with his master's degree in December. And he's going to be presenting his Globe. Actually, this is sort of an extended version of his GlobeCom talk on CRC-Aided short convolutional codes and RCU bounds for orthogonal signaling. Go ahead, Jacob.
All right. So yes, I'll be presenting our paper for GlobeCom 2022, which, as Professor Russell just said, is titled CRC-Aided Short Convolutional Codes and RCU Bounds for Orthogonal Signaling. I'll begin by defining a few terms. Signaling is said to be coherent if the local signal at the detector matches both the frequency and the phase of the incoming signal. In contrast, non-coherent signaling is when the local signal matches the frequency, but not the phase of the incoming signal. Phase coherence improves the performance of the receiver and is therefore necessary for optimal detection, but phase coherency can be difficult to achieve in practice. Good non-coherent signaling solutions are necessary for these situations. One such non-coherent solution uses orthogonal signaling. Two duration t signals, f of t and g of t, are said to be orthogonal if the integral of their product over the full duration is 0. One example of an orthogonal signal set are Hadamard sequences. Each row of the Hadamard matrix, seen here on the right, corresponds to one of the signals in the signal set. Notice that any two rows of the matrix are orthogonal to each other. Another example is Q-ary frequency shift keying, or QFSK. Each signal in the signal set takes the form of A cosine 2 pi FIT. These signals are all pairwise orthogonal if the differences between the frequencies Fi are multiples of the symbol rate 1 over t. This is the orthogonal signaling channel we will focus on for the remainder of this presentation. Orthogonal signaling is used in the Bluetooth standard and the Internet of Things protocol LoRa as a couple of examples. Many papers have shown that CRC-aided list decoding of binary convolutional codes performs very well on the BPSK channel. We build on this work and design Q-ary zero-state terminated convolutional codes concatenated with Q-ary CRC. We call this concatenated code a Q-ary CRC-ZTCC. Since we are working in a Q-ary alphabet rather than a binary one, all operations are done in the Galois field of Q elements, otherwise known as GFQ. We designed these CRC-ZTCCs in order to optimize the distance spectrum of the concatenated code. We present three main contributions in this presentation. We begin by describing an efficient search method to find optimal Q-ary CRCs for Q-ary ZTCCs and present the results of our search. We then derive the random coding union bound for the non-coherent QFSK channel. Finally, we present simulation results for our optimal CRC-ZTCCs on the non-coherent QFSK channel and compare these results with the RCU bound. Here we can see a block diagram of our system model. We begin with a K-symbol Q-ary message. This message is a string of K symbols from the Q-ary symbol alphabet 0, 1, etc. up to Q-1. This message is then passed through an M-symbol Q-ary CRC encoder. Once again, note that the arithmetic for this encoding is done in the finite field GFQ. Since it is an M-symbol CRC, the CRC encoding adds M symbols to our original message, resulting in a K plus M symbol CRC word. Our CRC encoder is systematic, which means that the original message appears as the first K symbols of the CRC word. In other words, the CRC encoding simply adds M symbols to the end of our Q-ary message. We then pass our CRC word through a Q-ary convolutional encoder to generate an N-symbol Q-ary CRC-ZTCC code word. We use a zero-terminated convolutional encoder, which means that we append new zeros to the end of our CRC word before encoding. Here, new is the number of memory elements of the convolutional encoder. The result is an N-symbol CRC-ZTCC code word. We then map our code word symbols to a signal for transmission over the channel. We use QFSK as our modulation scheme, meaning that we have a set of Q signals denoted S sub 0, S sub 1, up to S sub Q minus 1. Each signal takes the form of A cosine omega IT plus phi. The magnitude A and duration T of these signals are chosen so that the signal has total energy E sub S. Since we have non-coherent reception, we also model phi as a random variable that is uniform on the interval 0 to 2 pi, and phi is unknown to the receiver. To ensure pairwise orthogonality between each signal in the signal set, we separate each frequency by multiples of the symbol rate 1 over t. We map each CRC-ZTCC code word symbol directly to its corresponding frequency. That is, if the ith symbol of the code word is k, then the ith signal transmit is S sub k. This maps all n symbols of the code word to a sequence of n signals. These signals are transmit in series over an AWGN channel with zero mean and power spectral density n naught over 2. This results in a sequence of n noisy signals, where a noise signal Ni of t is added to each transmit signal Si of t phi. These noisy signals are received in series by the non-coherent receiver. The non-coherent receiver consists of a total of Q correlator banks, one for each signal in our signal set. On the right, we can see an example of one of these correlator banks for the 0th signal S sub 0, excuse me. Again, the phase of the signal being received is unknown. So the correlator bank begins by performing two correlations, correlating the received signal R of t with S sub 0 and phase 0, and correlating R of t with S sub 0 and phase pi over 2. The root sum square is then taken of the results of these correlations. The root sum square is equivalent to computing the magnitude of a point in 2D space, where the coordinates of this point are the outputs of the correlations. Doing this for all correlator banks results in an output vector y, consisting of one output y sub I for each correlator bank. In the absence of coding, these magnitudes are then used to make a decision on what symbol was sent. However, since we are using coding, these magnitudes are instead passed as metrics to our decoder. Let's assume that the transmit signal was S sub I of t phi. For correlator bank J, if I does not equal J, then the correlation of S sub I with S sub J will be 0 due to the orthogonality of the signals in our signal set. As a result, the jth correlator bank will only correlate with the noise signal N of t, and the output Y sub J will therefore be a Rayleigh distributed random variable. However, if I does equal J, then the correlation of S sub I and S sub J will not be 0. Because of this, the jth correlator bank will correlate with both the transmit signal and the noise signal, resulting instead in a Rice distributed random variable. Here we can see the probability density functions for the Rayleigh and Rice random variables, where I sub 0 is the 0th order modified Bessel function of the first kind in this equation. In our model, the parameters mu and sigma squared take the value 2 ES over N naught. The random vector Y consists of one Rice and Q minus 1 Rayleigh random variables, since the transmit signal always correlates with exactly one correlator bank in the detector. Thus, the probability density function of Y is the product of the PDFs of one Rice and Q minus 1 Rayleigh random variables, and we can see the channel equation that is generated by that here. The receiver outputs a series n random vectors y1 to yn. These vectors are then used as metrics for the List-Viterbi algorithm decoder, or LVA decoder. This is the maximum likelihood list decoder for CRC-ZTCCs. We also choose to use an adaptive LVA decoder. The block diagram of the adaptive LVA decoder is shown here. We begin by initializing the list size to 1 and running a parallel LVA decoder with this list size. We then check if the decoder has found a code word that passes the CRC check. If one does, then we select that code word and terminate the decoder. Otherwise, we double the list size and run another parallel LVA decoder with the new list size. This continues until either a code word is found that passes the CRC check or until the maximum list size is reached. Here, maximum list size is a hyperparameter set before decoding. We now describe how we design optimal CRC convolutional concatenated codes. For a given block code, if n of d is the number of code words with Hamming weight d, and p sub 2 of d is the pairwise error probability between two code words a distance d apart, then the probability of code word error is union bounded by this equation, where we sum the product of these values over all weights d. At high SNR, this union bound becomes dominated by low weight code words. Because of this, in order to minimize this union bound at high SNR, we want to make the minimum distance of the code as large as possible, and also have as few code words as possible at this minimum distance. We call codes with this property distance spectrum optimal, or DSO. Ryan and Wilson have found Q-ary convolutional codes for small memory that optimize the information weight spectrum of the convolutional code, which is similar to distance spectrum optimal for block codes. We design distance spectrum optimal Q-ary CRCs for two Q-ary convolutional codes from Ryan and Wilson. Liu et al. Have presented an efficient search algorithm for finding distance spectrum optimal CRCs for binary zero-terminated convolutional codes. We use the same method as Liu, adapted for Q-ary codes and arithmetic in GFQ. For a convolutional code with polynomials g1 of x and g2 of x, and an m-bit CRC with polynomial g of x, we consider the equivalent catastrophic convolutional code with polynomials g1 of x times g of x and g2 of x times g of x. We start by setting a maximum weight d tilde to search up to. We then search all paths in the trellis to find all code words with weight less than d tilde, terminating a path if the path weight ever reaches d tilde. We then do this for all possible m-bit CRC polynomials. That's a typo. It should say m symbol because we're in Q-ary alphabet, not binary. My bad. Once this search is finished, we select the CRC that generates the CRC-ZTCC with the largest d-min. If multiple CRCs tie for the largest d-min, we then select whichever CRC results in fewer code words at d-min. Here we can see the 4-ary convolutional codes we used in table 1 and the corresponding 4-ary distance spectrum optimal CRCs in table 2. This column on the left shows the coefficients of the DSO CRC polynomials. Here, alpha is the primitive element of GF4 and beta equals alpha squared. To the right, we can see the minimum distance of the CRC-ZTCC concatenated code. The column n sub t of d-min refers to the number of trellis paths that start and eventually return to the zero state of the trellis with weight d-min, and n sub c of d-min refers to the number of code words of the length n CRC-ZTCC block code with weight d-min. Each code word of n sub c consists of one of the trellis paths of n sub t, with the rest of the code word consisting of zeros. As such, n sub c can be thought of as the number of offsets that the trellis paths in n sub t can take within the length n code word. We'll now discuss the random coding union bound, or the RCU bound. The RCU bound was first presented in 2010 by Polyansky, Poor, and Verdu. It is an achievability bound on the error rate for codes of a given finite block length and code rate across a given channel. That is, there exists a code that can do at least as well as the RCU bound at that block length and code rate. While the RCU bound is an achievability bound, in practice it is very difficult to find block codes that can beat the RCU bound. Recent results by Yang et al. Have found tail-biting convolutional codes with CRC that can beat this bound. The exact calculation of the RCU bound is intractable for most practical block lengths. As a result, we instead use a saddle point approximation of the RCU bound for our non-coherent Q-ary orthogonal channel. Fonsegura et al. Presented a saddle point approximation for the RCU bound in 2018. We take their derived equations and modify them for use for the non-coherent QFSK channel and Q-area codes. Unfortunately, going through the full process of this derivation and modification of these equations will take far more time than I have. The full set of equations is in the accompanying paper, but for now, we'll highlight a couple important details about our derivation for this saddle point approximation. First, several equations for the saddle point approximation require the channel equation. We derived this channel equation previously, and is the product of the PDFs of one Rice and Q-1 Rayleigh random variables. And we can again see the channel equation here. Second, a couple equations also require integrating over the full domain of the channel output. For our case, the channel output is our random vector Y, which is the outputs of all of the correlator banks. So we must perform numerical integration over the vector space RQ plus, or the space of all length Q vectors with all positive elements. While the calculation of the saddle point approximation of the RCU bound is less complex to calculate than the true value, it is still very difficult to compute. This is largely due to the multidimensional numerical integration we just mentioned. In addition, one step of the calculation requires solving a multidimensional integral equation for a variable that is in the integrand. And this is extremely computationally costly to do. In contrast, the normal approximation is much easier to calculate, relying only on channel capacity C and channel dispersion V. Both of these values are known for this channel and are easy to find via numerical integration. As such, we compare our CRC ZTCCs to both the RCU bound and the normal approximation. At this point, we present the results of simulating our optimal CRC ZTCCs. We focus on Q equals 4 rate 1/2 ZTCCs in our designs. Our CRC ZTCC has an overall rate of K over 2 times K plus M plus nu. Here, M bits are added to the message for CRC encoding, sorry, M symbols, my bad. And new zeros are appended for zero termination. We use a message length of K equals 64 4-ary symbols in our simulations. And our LVA decoder has a maximum list size of Lmax equals 2048. Our codes have different code rates with different length CRCs, so all of our plots compare against EV over N naught, which adjusts for different code rates. This plot here shows the frame error rate curves of all memory 2 CRC ZTCCs that we found. Solid lines on this plot correspond to the CRC ZTCCs, and the dashed lines correspond to the normal approximation and RCU bound. The M equals 0 curve on the far right is for the ZTCC with no CRC encoding. That is a 0-bit CRC. We can see that increasing M improves performance of the CRC ZTCC, but seems to have diminishing returns at higher values. We now show the FER curves for all memory 4 CRC ZTCCs. We can see that these codes perform significantly better to the memory 2 counterparts and approach fairly close.
Can you just toggle back and forth between the two slides for just a second?
Yeah, sure. You can see that they perform significantly better than the memory 2, and also approach fairly close to the RCU bound. We now plot each code's gap to the RCU bound in dB versus frame error rate. On this plot, solid lines correspond to the memory 2 codes and dashed lines are for memory 4 codes. We can see that the best memory 2 CRC ZTCC, which is a little hard to see behind all the lines there, but it's the magenta line. It has a gap to RCU bound of around 1 dB at a frame error rate of 10 to the minus 4. The best memory 4 CRC ZTCC does better with a gap of around 0.6 dB at FER equals 10 to the minus 4.
Now, did you just only go up to M equals 7 for V equals 4 as opposed to M equals 8?
Yeah, because the complexity scales exponentially with constraint length, and the constraint length of the concatenated code, or like the catastrophic convolutional code, is nu times M. or
Are
new
you
plus
talking
m,
about
sorry.
the complexity to find the CRC or the complexity
Yes,
to decode?
yes, to find the CRC.
Yeah.
Anyway, yes, we had to stop at n equals 7 for complexity reasons on
For now,
memory
maybe
4.
we'll,
For now.
yeah, maybe that's something Holden will help us with later. Or he can carry on after you. Yeah.
This 0.6 dB gap is consistent with results for binary CRC ZTCCs in Yang et al. We also plot the expected list size of the LVA decoder against EB over N naught for the memory 4 CRC ZTCCs. We see that at high EB over N naught, the expected list size converges very quickly to 1. In addition, at low EB over N naught, the expected list size converges to 4 to the power m, except for the case where we are limited by our maximum list size of 2048. These results also match the results for binary CRC ZTCCs in Yang. In this presentation, we present CRC ZTCC concatenated code designs for Q-ary orthogonal signaling by designing Q-ary distance spectrum optimal CRCs for specific ZTCCs. We also derive a saddle point approximation for the RCU bound for the non-coherent QFSK orthogonal channel, and we compare the performance of our CRC ZTCCs to this bound. Our best designs have a gap to RCU bound of around 0.6 dB at FER equals 10 to the minus 4. Binary tail-biting convolutional codes with CRC have also been shown to outperform CRC ZTCCs, approaching very close to and even surpassing the RCU bound at short block lengths. Future work will extend the work here to designs of CRC TBCCs and explore higher values of Q. That finishes up my presentation. Thank you all for watching. I'll now take any questions.
Well done. That was a great talk. I mean, I have to say, yeah, I'm really, here, let me put my clapping icon there, but I'm really, really impressed with how clearly you explained. You didn't leave anything, you didn't skip the basic stuff that our audience needs to understand to follow what's going on, but you managed to get it all. I really did not believe, I thought you, since you had 90 slides, that you would be running. Yeah, well done.
Thank you.
I'd like to take a moment and let people ask questions. And Chester, I think you should ask Jacob whether or not he is using Wava as a pre-processing step and explain to him what you found in the last few days.
I guess we can start with that. I was just using the Wava approach and simulating it versus no Wava, and it seemed like Wava no Wava never beat Wava, even as I increased SNR or decreased it or increased and decreased list size. And for those who don't know, Wava is just initializing metrics differently when you use list Viterbi decoding. So yeah, I was wondering if you used it and if you had similar results or tried testing that.
So were you using Wava with zero terminated convolutional codes?
No, it was just
yeah.
tail biting. So yeah,
I was going to say that Wava is something for tail biting, as far as I know.
That's a good point.
That's right. I'm sorry. I guess it's not a question for this talk. It's a question for stuff you're about to do.
It's relevant for the other projects I'm working on.
Are you using Wava for the tail biting work?
I believe, because based on Bill's simulator, I believe he does a single pass through to initialize the metrics.
That's correct.
Rather than a full Wava.
Oh, I think that's what, Chester, is that what you were looking at too?
Yeah, I'm also going to simulate a couple pass-throughs, but for now it's just one. Yeah.
Well, we're getting, I guess that our recent data shows that is a really smart thing to do to get better performance. So good. Let's open it up for other questions.
I have a question.
Yes.
So we've seen in other, I think it was one of Henry's presentation, that at some point as the CRC length grows, you start decreasing the performance. And in your plot, it seems that the performance keeps improving. So in page 85, for instance, you can see clearly that the performance improves as the length increases. So for how long? So it seems that you're having trouble like simulating larger sizes, but it also seems that it is worth doing, because so far we only see increases there. Like, do you have any thoughts about it?
So we do see, for the ones that we found, we do see increases. However, at the very end, like the largest values we signed, the increases seem to just about stop. Like if you look at our plot right here at the very bottom, the yellow and black dashed curves lie basically on top of each other. So it seems.
Oh, okay.
That,
I didn't see the yellow one. Okay.
yeah, it's a little more obvious if we look at the frame error rate curves, I think, where, you know, at the start, you know, increasing from n equals 3 to n equals 4 does have a noticeable increase. But once we get up to m equals 6 and m equals 7, they're lying just about on top of each other. I don't want to extrapolate without the data to back it up, but I wouldn't be surprised if it matches Hung Jae's results of it starts doing worse once we go up too high.
Or at least diminishing returns. Can you show us the, do you see the same diminishing returns clearly for the memory 2 case?
Yes.
Yeah, that's a really good answer. I was looking for that diminishing return, but I skipped the yellow line. I couldn't see it. Okay, and one more question. Are there more than one CRCs with the same minimum distance that might make it worth it to look at other distances, like the total distance spectrum?
Yes, that can absolutely be the case. Maximizing the minimum distance, like looking at only the minimum distance, is not the be all end all for getting the best possible performance, but it does make it easier to or faster rather to find these CRCs. Because if we have to look at a more extended distance spectrum, that means we have to do more calculations to figure out which CRC is the best, and that can take longer, especially when you get up to higher and higher values of M, where when you're comparing all the CRCs, you get exponential complexity.
We're actually going to have Jacob, we might have to have you come back again and talk about the comparison with polar codes. Because the distance spectrum perspective, it's just fascinating when you look at this particular low rate 32 over 512 code, comparing polar and convolutional, and the distance spectrums are very different. But the frame error rates aren't that different. But for the convolutional codes, I was looking at recently you did some optimizations there and reduced the number of minimum distance code words from 4 to 1. But I was wondering about what about the overall distance spectrum? Like, did it actually get better, or were the changes minimal? And I don't know the answer to that, but I think it's, I do think we have a sandbox in which we could play around with Amael's question.
Yeah, it's also a bit different. It's interesting you bring that up. For this case right here, I'm going to go back to here. If you look at our D-mins, you can see like all of them are in between 10 and 20 for the D-min of the concatenated code, which is pretty small for this purpose. And what that means,
better than 6.
Yeah, better than 6. But what that means is we don't have to look very far past the minimum distance before the terms start being irrelevant. For the case that you're mentioning, which is the super low rate 32 over 512 codes, the minimum distance is around 130 for those. And that means that you have to go out a large number of distances past minimum distance, and they still have a non-negligible impact on the union bound. And so that means that in that case, maximizing the minimum distance is even less of the be all end all than it is in this case. You have to, if you really want to be fully optimal, you need to look at, 20, 30 distances past the D-min of 130 to be truly confident. And then that requires calculating the distance spectrum for every CRC out that many distances. And that's hugely computationally complex. Luckily for that case, we have a very short block length of 32, or message length rather, of 32 bits. So we can just brute force find every single code word for some of the CRCs and get the full distance spectrum. But if we wanted to compare the full distance spectrum of every CRC, it would be very computationally complex. Like just a rough estimate based on what I had, it would take around a month and a half on my computer.
So very interesting. So I guess we use this term distance spectrum optimal, and sometimes we end up just maximizing the minimum distance. Really what we want to do is find the CRC that gives us the best union bound at a particular operating point.
Yes.
That's the actual goal. Oh, Hung-Jae, do you have a question?
Yes. So I'm wondering what's the benefit of using a large value of Q?
Larger Q means you can increase your symbol rate. You can send more bits per channel use. I know that larger values of Q is also what's more generally used in practice. I think there are some 16 ARRI and 64 ARRI channels that Bill is interested in, and codes for those channels.
In a sense, Hung-Jae, the Q is something that's given to us from the system. Like if I have 16 frequencies that I'm allowed to transmit on, then Q is 16. And it's better. And if I have the availability, if you give me 16 frequencies, then I wouldn't just transmit on 4 of them with Q equals 4, because then I'm leaving, 75% of my bandwidth, just leaving it on the table. So generally speaking, we'll figure out what the Q is that our system is going to support and then design the code for that Q. Right now, we're starting with artificially small Qs because Jacob is learning how to walk before he runs, basically.
It's also the calculation of the RCU bound scales like faster than exponentially with Q.
Jacob, I want to mention to you, there's a paper that you need to read. Well, I don't know if you'll have time to do this before you complete your master's degree, but our colleague and coworker, actually a collaborator of Hung-Jae's and mine from Caltech, has developed a new way of computing. It's like a simpler version of the RCU bound that's better and simpler. So, and I'm not sure whether that applies to the orthogonal signaling case or not, but if it did, that I guess that would really, if we were able to add that, that would make a very strong, IT paper that, kind of like would be the icing on the cake to include that additional bound. So I just want to make sure that you're aware of that and that we keep that in mind, whoever continues this line of research.
Yeah, if you could please send me that paper, I'd love to read that.
I also have another question. So in terms of approaching the RCU bound, so does having a bigger value of Q help?
I'm not sure I understand
what
what you
I'm saying
mean.
is, if you have a large value of Q, will you be more easily to approach the corresponding RCU bound? Or
At this point, I don't know. I've only simulated codes and found the RCU bound for the Q equals 4 case. The techniques I have are general to all Q, but complexity does become an issue with higher Q.
Capacity increases as you increase Q, and in fact, everything heads towards the Shannon limit of minus 1.6 dB as Q heads towards infinity. So so the capacity increases now. But as far as the RCU bound is concerned, it's different for different Q, right? And so and it's also much more difficult to calculate for Jacob. It gets very difficult.
Yeah, I'm really interested in like whether the gap to RCU bound diminishes as Q increases.
Yeah.
Yeah, I'm working on getting those results for higher Q right now.
Okay.
And for
Jacob.
tail biting. Both of those, we're really interested in getting those results, both of which will be interesting because we
Mhm.
expect to see smaller gaps when we introduce tail biting, just like you saw for the binary case, Hung Jae. And
Yeah.
then, well, we'll just have to see what happens with the larger values of Q. But
Okay.
even if we're similarly close, like if you do tail biting in large Q and you're basically on top of the RCU bound, then that has really exciting practical implications.
Yes.
Hey, Jacob, you plotted expected list size against SNR, EB over 0. I was wondering what it is at 10 to the minus 4, FER equals 10 to the minus 4. Some of these list sizes.
I have a plot for that. It's not in this presentation.
Let me see.
Give me a
Well,
second.
you can just pick off. Okay.
Oh, I see. We can just look at
Yeah.
here.
Yeah. That one.
So 10 to the minus 4 is around what, 6.2, 6.15 dB.
Yeah.
So that's, it's in between 1 and 2 for the, okay. Your expected list size does get higher with longer CRCs because it clears out more code words. But even for our highest one, it's an average list size of around 2 at 10 to the minus 4.
Okay. Thank you.
You're not showing m equals 7 on this plot though.
Yeah.
Yeah.
So it might be.
Yeah, I think I made
closer to-
this plot before I finished finding the m equals 7 curve, but also our maximum list size is at the top here, so it would look very similar to the m equals 7 up here at least, just because we'd be limited by our maximum list size.
So it could be 3 or 4, let's say.
Yeah.
Okay. Thank you.
It's really, I think that's one of the most exciting things about the list decoding is that although it conceptually could be very complex to decode to go through that list, when you look at what's actually happening at the operating point you care about, it's not that bad. Or you rarely have to go deep into the list. Can you back up a couple more slides?
To which one?
I think this is, yeah, it's really, go to slide 82, I guess, 82, okay. Because I think I'm just gonna make a comment to you for later that you could do what you've done, like just show me the v equals 2 curves, and then in a different slide, bring in the v equals 4 curves on top so people can see. That's okay. Okay. Do we have other questions?
Oh, I also have a comment on the plot. I think the plot looks pretty busy. And is there any way to make it much easier to read?
Yeah, that was, if we do what Wessel just suggested and kind of breaking this up into 2 separate plots, that'd be because like we could get rid of all the dashed lines on this plot and it would only show the solid one. And then on the next one, we would show only the dashed ones. And those would be like the fair comparisons for equivalent constraint length.
Yeah.
But yes, this plot is quite busy.
Yeah, if you do the same thing where you make a plot that has exactly the same X and Y axis and you can toggle back and forth, that'll make it really easy for people to see what's going on. So it seems like, I mean, there's a sense in which kind of the question is, well, should I do V equals, what if I do V equals 6? Does it help a lot more, or do I start to run into the limits of performance? Like I'm trading off between a larger V versus a larger M. It'll be interesting to see.
Yeah, it's unfortunately when you're searching for these optimal codes, complexity does scale exponentially as you increase things like that. So it does get hard to find it. Like as an example, like for memory 2, we can go up to a CRC length of 8, but for memory 4, I was only able to go up to 7 because trying to go up for 8 for memory 4 would have taken me like 3 weeks or something like that. I think that's an underestimate. It's hard complexity wise to find these optimal things, and it's even harder if you're also trying to find optimal convolutional code polynomials, because you have to care about every single pair of convolutional code polynomials for rate 1/2. So it's unfortunate how that works out, but I know some plots in Hung Jae's papers show that increasing constraint length does tend to increase performance. I can't remember if there's diminishing returns at the higher ones. Maybe he can answer, but yeah, this is just what I'm remembering.
Well, what we're not showing is we haven't brought complexity into these curves. So I think when you look at performance versus complexity, well, Hung Jae, what do you think when you think about the performance versus complexity plots? Is there sort of a limiting V where we really don't need to make it any larger?
Maybe there is a limit because we do see a trend of slowdown, right? Yeah, I'm just guessing, but we definitely need to do more simulation to verify that.
Okay. Well, are there any more questions? Okay, I'd like to thank Jacob again.
I think Emil has a question.
Oh, go ahead.
Yeah, so it seems to me that you're dealing only with zero terminated codes, and in that case, especially for short blocks, increasing V also increases the code word length. So that will be like a little bit of artifact when trying to see what the effect of increasing the code word length is versus increasing the let's say, I mean, the effect of the number of memory elements, basically how the code words vary. So I just was wondering, like, what do you expect? It seems to me like that if you are constrained by certain length, if you increase V, you might have to reduce M or something like that. What's your thought about it?
Yeah, if you want to keep equivalent code word lengths, if you increase V, you do have to reduce M for zero terminated. Tail biting doesn't have this problem, which is, I think, a large reason why tail biting does so much better than zero terminated. This paper focused on zero terminated because that was kind of the framework I had at the time for finding optimal CRCs. I have since then written search algorithms for tail biting, and we're working on getting results for tail biting for these cases.
Got it, thanks. So when you have those results, that will be a really like interesting fair comparison that will tell you what the actual effect of increasing memory size will be, I guess. Thanks.
Yeah. Lin Fong, did you have a question?
Yes. So just a comment. In the simulation part, could you please provide the K value and the N values? I think I didn't see the.
Yeah, sorry.
Oh, yeah.
Right
Okay,
here.
yeah. Okay, sorry, I just missed that. Thank you.
Yeah, no worries.
So K is equal to 64 and the N is varying slightly.
Yeah.
But I'm actually, I'm a little confused about the overall rate. I feel like maybe you need another parentheses. Is everything after the K the denominator?
Yes, sorry.
Yes.
You're
Yeah,
right. I should have put another set of
for your
parentheses.
presentation at GlobeCom, I'd like to see that as a fraction that has a
geez.
horizontal line.
Sorry
K
about that.
over, because it's really, it's roughly speaking a rate 1/2 code with a rate slightly less than 1/2 because of the CRC and because of the, well, actually more than slightly less than half, really. But you know, we have the termination and the CRC. So
Yeah,
And-
you're absolutely right. I should make that a fraction.
And the other thing I'm a little bit curious is in the simulation part, for different rates, the RCU bounds and the normal approximation bounds look overlapped. But I think the reason might be like you align everything using the AB over N node. But I don't know. Yeah, I'm just
Yeah, it's all of those curves are very slightly different
Okay.
because of every single different rate has a different bound. But the way
but
it
the
turns
rates
out,
are
So
changing.
is the
rates are
rate-
similar enough that it turns out not to matter.
Yes,
Mhm.
maybe the rate maybe the rates are too similar.
yeah,
Okay,
all
yeah.
the rates are extremely similar, so the bounds
Okay.
nearly coincide.
Okay, that makes sense.
In theory,
but-
they
but-
would be different, but in practice, they're not that different. So
Yeah.
we're just being extra cautious by plotting all of them.
Mhm.
Yeah.
But also you might increase minimum distance while lowering code rate. And it's that product
Right.
that gives you the
Mhm.
performance, R times D.
What's the code? What's the transmission rate for this system? The range.
I don't quite understand
I'm
what
just asking that what's the transmission rate of this system?
I think Lin Fong is asking you to take your rate and also take
Mhm.
into account like what is the symbol rate of real
Yeah.
systems that use
Yes.
it.
Yeah, so
Try to
that's
understand the actual speed like in a Bluetooth system.
So yeah,
Which you may
the
not
point of
know
my
because our
confusion
work
is, the
sort
point of my confusion is that this is for a abstract system. So symbol rate is determined by sorry.
If
Here we
Bill
go.
is allowed
Oh.
to, he could probably tell us
Mhm.
like what are the actual
I
transmission rate.
think what I'm asking is the spectral efficiency, the bits per channel use, like
Oh,
yeah,
so if yes.
I think it's K over N. The K over N. So if I just want to see because these curves are overlapped together. I just want to see what's the range of all these rates. They should look very similar, right?
Yeah, I don't have
Yeah.
any plots for
Okay,
that,
sure.
but yeah, like
Mhm.
for Q equals 4, for example, we're sending 2 bits per channel usage because we're encoding 2 bits into one 4-ary symbol. And in general, for any Q, we're sending 2 to the
So the bits per channel
log
use
Q,
would be-
rather, log 2 of Q.
the bits per channel use would be exactly that. It would be the rate.
Yeah.
Mhm.
Jacob,
I think it
roughly speaking, a half times log of Q bits.
Yes.
So on, rough numbers for a Q equals 16 system, which I guess is a practical system where they're using 16 frequencies, the actual information rate is something like 7 or 8 bits per channel use.
Mhm.
Bill, is that consistent with your thinking?
yeah.
You 7 or 8 bits for not for this though, right? Not for.
Oh, no,
this
I'm sorry, I
Q.
got it wrong. If Q equals 16, log base 2 of 16 is 4 bits.
4.
So it would be like between
be
1
more
and a
like
half
2
and
bits.
2 bits.
Yeah.
Yeah, that's right.
Yeah, sorry. Yeah.
Jacob, what's the separation between the frequencies in terms of symbol rate?
I mean, the most optimal one is separating them all by 1 over T, if I understand it correctly, but
because you're using non-coherent rather than coherent, yeah. So the throughput of this system will be low because you're occupying lots of bandwidth. Yeah, as Bill Ryan said that essentially, if you increase the Q number of frequencies, you get the Shannon limit because your throughput is going down, your overall code rate goes down to 0 as Q increases, right?
Right, yeah.
So you get EB over N0 minus roughly 1.59, something like that.
Mhm.
All right. Are there any more questions? Okay, well, thank you. It's a good thing that your talk was as short as it was because we had a significant number of questions and a great conversation. And it's just a sign that we're sort of building a community of list decoding experts. So it was really fun, Jacob. And let me thank you again for a great presentation. And we will, yeah, so hopefully we'll get to have you come back and tell us about your other work and the updates on this work, maybe even after you're working full-time at Zeta. Maybe they'll find time to let you come back and give another talk. But with that, I think I'm gonna go ahead and stop the recording. So thank you, Jacob, and this is gonna conclude the recorded portion.